We're having a look at the pigeonhole principle, and it's really, really simple in theory, but it gets complicated when you try and talk about it in practice. So we're going to go through quite a few examples for this one. So first of all, let's talk about what the pigeonhole principle is. Let's say I'm a weird person and I have pigeons, because, you know, who doesn't have pigeons, yeah? And I have like 3 pigeonholes for them to come and roost in. So I've got 4 spots for them to come and have a nap. I mean 3 spots for them to come and have a nap, obviously. But let's say I have, that's supposed to be a pigeon. That's I don't know what's going on with that. Let's pretend that I have 1, 2, 3, 4 pigeons. If I have 4 pigeons, then I actually, hang on. If I have my 4 pigeons, then 1 will go here, 1 will go here, 1 will go here. The 4th one must have to bunk up with another. So that means there is at least 1 pigeonhole with 2 pigeons in it. I mean, it also could have ended up with, you know, what's going on? 1 pigeonhole could have had like all 4 in it, which is fine. Or I could have ended up with 1 pigeonhole with 2 and another with 2. But that's less important. The whole idea between the pigeonhole theory is that at least 1 pigeonhole had to have 2 pigeons in it. Let's look at a different kind of question. Let's say that I've got some cake. And that cake, I've got 4 colours to play with. That cake, and I've got 1, 2, 3, 4, 5, 6, 7, 8 pieces. And let's say I've got 7 annoying children at my party. 4, 5, 6, 7. So we've got 7 kids, 8 pieces of cake. At least 1 kid has to get more than 1 piece of cake. 1, 2, 3, 4, 5, 6, 7. Well, 1 kid must have to get 2. Or 2 kids could get 2 and then another kid misses out. The whole point is that at least 1 kid has to have more than 1 piece of cake. That's kind of it. So let's have a look at the first example now. 70 guests sit at a restaurant with 23 tables. Prove that there must be 1 table with at least 4 guests. Let me get some lines on this page. I work best with lines. Okay. So we've got 70 guests at a table with 23, at a restaurant with 23 tables. So we've got 1, 2, 3, 4, 5. I'm not going to draw these all. You do not need to draw these all. But I also know that 70 is 23 times, well, calculator. 70 divided by 23 is 3.04, yeah? Let me get rid of this. So 70 divided by 23 equals 3 and a bit. The and a bit is what's important, because if I have 23 tables each with 3 people, then that's 23 times 3, which comes out as 69. So 1 extra person, because we have 70 people, which means 1 table must have at least 4 guests. Now, we could have had like a table with 8 people and then some others with only 2 or 1. That's fine. The whole point is that there's at least 1 table with at least 4 guests. Because if they didn't, all the tables would only have 3 guests, which means we'd only have 69 people taken care of, or less. But we've got 70 guests. For part B, explain how many guests there must be to guarantee that at least one of the 23 tables has at least 11 guests. So, if they all have to have at least, well, if one of them has to have at least 11 guests, and we're assuming they're evenly spread, otherwise it's even less. Well, 23 times 10 people is 230. So if we had 231 people, then at least one table would be forced to have 11 people. Or more. Must have 11 people or more. Okay, let's have a look. I'm just going to pull up the textbook. Let's have a look at the next kind of question you'll get. Using division with remainder in the Pigeonhole Principle. Which is kind of what we did. It's kind of my approach for all of these. Okay, sorry about that. I'm back. So this time, and we're just going to talk about these. I'm not going to talk about what this seems to mean. This time, we've got 15 large apartment blocks in this suburb. We've got 15 large apartment blocks, and the first question says, if a shopkeeper knows 200 people from these blocks, explain why he must know at least 14 people from at least one block. Well, if we assumed that they were kind of evenly distributed, and we did 14 people were in 13 people, so if we assumed less than 14, if we did 13 people in each block, 13 times 15 is going to come out as 195. But he knows 200 people. So in this case, we have 5 extra people. So we've either got 5 blocks with 14 or some with 15, some with less than 13. It'll all even up. So at least one block has to have more than 13. 14 is the next number that's more than 13. You can't know 13 and a half people. Therefore, he must know at least 14 from one block. Another way to approach that same question is to say 200 divided by 13. Sorry, no, divided by 15. We're going to divide by how many blocks there are. $13 and a bit. It's the and a bit, which means therefore more, 14 and more, 14 or more in some blocks. That must make sense, yeah? That makes more sense than doing it the other way, I think. I'm going to do it that way from now on. Next question says, how many people from these blocks must he know in order to know at least 25 people from at least one block? Well, we've got 15 blocks. We're going to assume, well, if he doesn't know at least 25, then it's 24. So if we've got 15 times 24, that's 360. So if he knows 361 people, then at least 25 of them have to be from one block. (361 people), then at least 25 must be from one block. Let's have a look at another question like these. Actually, I might save this for the next video. Watch the next video. We're just going to go through heaps of examples like this and talk them out.